Hello, this is Joe Shooter. I'm presenting my final case study for Machine Learning 2 on Levenshtein distance and cosine similarity. For the presentation today, we are covering edit distance or Levenshtein distance compared to cosine similarity. Both are used in natural language processing to determine if things are the same or different than each other. Edit distance or Levenshtein distance is generally used to compare two strings or words to one another by counting the number of operations that would be required to transform one string to another. While cosine similarity is usually used to compare one document to another, so multiple sentences in each document to each other, and it does that by counting the occurrences of words in each document and converts those to vectors to do some comparison. The reason that I'm looking into this topic is I'm attempting to build a data pipeline where I would like to be able to convert similar words into kind of a common dictionary of words. For example, I work in the airline industry, so I'm attempting to, for example, merge American Airlines and American Eagle into one common American entity. Starting with Levenshtein distance, the intuition behind this is Levenshtein distance is trying to tell you the number of differences between two strings. The higher the number, the more different the strings are from each other. In a simple example like kitten and sitting, the Levenshtein number is 3, since there are 3 edits required to change kitten to sitting. So the first substitution is an S for the K. The second substitution would be an E for an I. And then the third substitution is adding a G at the end. So an edit is defined in this case as either insertion, deletion, or replacement of characters. Very typically, the edit distance is visualized as a tabular format with one string going down the left-hand side and the other string going across the top, with the diagonal showing the distance of the two strings as we move from character to character. In this particular example that we've already been looking at, sitting and kitten, we can see that the diagonal starts off right away with one difference with the S and the K, and then there are no changes for quite some time until we get to the I and the E. So the difference increments to 2 at this point, and then there is no difference here with the ends, but finally at the end a G is added, bringing the total distance to 3. Here's another example where we're comparing two strings, in this case 2 days of the week, Sunday and Saturday. We start in the upper left where S is equal to S, so the difference is 0. We're inserting an A, the difference becomes 1. Inserting a T, the difference becomes 2. U is equal to U, so the difference remains at 2. We substitute an R for the A, so the difference goes to 3. And all of the rest of the characters are the same, so the difference remains 3 for these two strings. This visual shows how to compute the minimum edit distance in a slightly different way. It shows having the two words laid out in a spreadsheet format and trying to match them up that way, showing the differences in a slightly more linear fashion. You can see along the bottom that there are deletions, substitutions, and insertions. The distance would be either 5 or 8 depending on sometimes substitutions cost more. Here we're showing the math behind Levenshtein distance. The math or the equation behind the Levenshtein distance is actually somewhat of some conditional logic. If either of the strings being compared are 0, the distance is the length of the other string. Otherwise, if the characters or the strings are both not 0, then we have some additional conditional logic where we're looking at strings character by character until they're not equal, and then determining if they are a insert, substitution, or a deletion, and adding 1 for that. Taking the equation from the previous slide, here we are converting that into a more algorithmic or programmatic way of determining the distance between the two strings. We can see here in step 1, we're getting the lengths of the strings, and if either are 0, we return the length of the non-zero string. And if both are not equal to 0, then we construct a matrix with the length times the width being the length of the two strings. Do an initialization, and then examine each character of each string and compare them to each other. If they're equal, the cost is 0. If they're not equal, the cost is 1, eventually ending up with a total distance of all the differences in the bottom right corner. An adjacent calculation to edit distance is cosine similarity. This visualization shows what cosine similarity is as opposed to Euclidean distance, which is yet a third measure of distance used in machine learning. The cosine similarity attempts to show an angle between two different matrices. So in cosine similarity, we build a matrix of our text, and then we attempt to calculate how far apart they are based off of an angle versus a absolute distance. Here we're showing the cosine similarity math, where we have two vectors, x and y. We're doing some calculations where we multiply the vector of x times y, and then divided by the square root of x times itself times the square root of y times itself to get to what the cosine similarity is. Also showing here how that might be done in code. Now we're ready to look at an example of calculating cosine similarity. In this case, we have two documents with multiple words in them, and we're comparing how closely they are related to each other. So the first document says deep learning can be hard. The second document says deep learning can be simple. In order to do our calculation, we must take those two documents and vectorize the contents of those documents. Here we can see down on the left-hand side of the table, we have all the words that are in both documents and the number of occurrences that word has in each document. Since we have vectorized the two sentences, now we can calculate the cosine similarity. Here you can see we take the dot product of the vector A and the vector B, getting 4, calculating the magnitude of vector A and also B, since they are the same. they're both equal to 2.23, and then you multiply the dot product divided by the two magnitudes multiplied by each other to get to an 80% similarity between the sentences in both documents. Comparing cosine similarity and Levenshtein distance at a high level, cosine similarity is generally used to compare two documents to each other, trying to get the similarity by counts of similar words, while Levenshtein distance is usually used in string comparison, trying to get a similarity between individual words, not all words in a document. So the intended use cases or the usual use cases are slightly different. Even though most data scientists use Levenshtein distance and cosine similarity for different purposes, let's compare them on how they do with string comparison. In this case, we did Levenshtein and cosine similarity on two sets of strings. You can see the first one was kitten and smitten, where the Levenshtein distance is 2. And then the second one is Lauren and Emma, where the Levenshtein distance is 6. Kind of hacking together, converting Levenshtein distance to a percentage, we get that kitten and smitten are 85% the same, while Lauren and Emma are 25% the same. Using cosine similarity math, we get very similar numbers where kitten and smitten in that calculation are about 83% the same, and Lauren and Emma are 33% the same. Our original question that we wanted to answer at the beginning of this was, is Levenshtein distance or cosine similarity the better of the two options to build fuzzy logic into a data pipeline? Answering that question strictly, it seems like Levenshtein distance is more appropriate and was built for that purpose. However, there are many other alternatives out in the deep learning space. In addition to Levenshtein distance and cosine similarity, there are a number of other options that are prevalent in the machine learning space today. I've listed a few of them here, like bag of words, word2vec, and glove, with additional distance measures like variation, autoencoder, and Siamese, Manhattan, and LSTMs. All of these solutions give even better results because they take into account semantics and meanings of documents.